Hi everybody, and welcome to my video for Lab 4 for Physics 20-11. The purpose of this lab was to compare the motion of the predicted model and observed motion of a spring mass system moving in the x and y direction. Then we had to plot the energy changes computed in the model, including the kinetic energy, gravitational potential energy, change in spring potential energy, and change in total kinetic energy. The results of this lab found that the change in energy was zero because this is a closed system, and the model overpredicted the motion of the spring mass system as compared to the observational data. The physics principles involved in this lab were Newton's second law, spring force, gravitational force, and the energy principle. Newton's second law was rearranged to find the final velocity and final positions of the system, and the net force was calculated by adding up all the forces acting on the system, which in this case were the spring force and the gravitational force. The spring force was calculated using Hooke's law, and the gravitational force was approximated as negative mg since the system was close to the surface of the Earth. In this system, the change in energy should be zero since it's a closed system. The change in energy was equal to the change in kinetic energy plus the change in potential energy. The potential energy was made up of the gravitational potential energy, which is equal to m times g times the distance y, and the spring potential energy, which is equal to 1/2 times the spring stiffness constant times the distance squared. The initialization values for this lab were as follows. The calibration length was 0.7 meters, and the frame rate was 10.5 FPS, and the mass was 0.402 kilograms, and all of these values were given in the lecture videos. The coordinate axis was set so that positive y faced up and positive x pointed to the right. The initial position vector and the average length of the time period were found using the tracker data analysis. The spring stiffness was found by using the formula 4pi squared times mass over time squared and was 5.97 newtons per meter. The relaxed spring length was found by setting the magnitude of the gravitational energy equal to the magnitude of the spring energy. This value was 0.4 meters. Here's a video of my tracker data analysis. You can see in the top right corner of the position data being plotted as a function of time. The values in the chart in the bottom right were exported as a CSV file to be used in the Python code. The initialization for the Python code included the mass of the ball and the initial position vector. The spring stiffness and relaxed length of the spring were inserted from the values calculated earlier. The equations for L, L hat, and S were also updated to reflect the correct calculations. In this slide, the system energies were computed by inputting the correct formulas into the Python code. In the first loop, Newton's second law was used to update the velocity and position of the system, and the spring was also updated by inputting the correct equations for L, L hat, and S. The second image was the code used to calculate the various system energies, including kinetic energy, gravitational potential energy, and spring potential energy. Lastly, the arrows were drawn to help visualize the motion of the system. Here's the result from the Python code. In this video, the kinetic energy is represented by the blue line, the gravitational potential energy is red, the spring potential energy is green, and the total energy is the yellow line. This is the Python result for the graph of the motion of the model prediction in blue and the observed data in red. The results of this lab demonstrate the change in energy is zero because the system is closed. This was visualized by the yellow line in the results of the Python code. As the kinetic energy increases, the spring potential energy decreases, so these values cancel out. The position of the observed data in the model data start out the same, but as time progresses, they get more and more out of sync. This is because for every 1 point from the observed data, there are many more points for the model, and the model doesn't take into account the effects of air resistance / drag. This causes the model to overpredict the motion of the spring. To answer the first question, yes, the energy principle is satisfied. The sum of all the energies acting on the system should be 0, so there is no energy gained or lost from the system. The graph from the Python code shows this because we see the yellow line, which represents the total energy, remains at 0 for the duration. To answer the second question, the time period would be calculated using the formula seen to the right, but in this case, we use the position data points for the x and y direction to determine the period. The period from the x position data was 0.71, and for the y position data, it was 0.76. These values are pretty close, but the vertical y value depends on the spring constant, and the horizontal x value depends on the force of gravity. Thank you for watching this video.